We will prove what is the volume of a sphere with radius r. So notice in particular we're doing this in the general case for any radius r. Okay. So how do you do this? What's the first thing that you need? Well, you need an equation. We need to describe this mathematically. So what's the equation that we're going to use for a sphere? Yeah, exactly. We're going to write down the formula for the line that's the circumference, and then how do you make, which is like a semicircle, and then how do you make a sphere out of that? Exactly, you rotate it. Okay. So the picture looks like this. Okay. And then we're going to rotate it. So when you rotate it, you wind up with this, and we're rotating it around the x-axis. So we're just using dx because that's the sort of thing we're familiar with. So if you take a little dx slice, what happens to that slice? Spins around like that. There you go. No, there, we don't need that. Okay.
Could you also use slicing in the x direction?
Could you? I'm sorry.
Could you also slice in the x direction too, like make it?
You mean make slices that are horizontal?
Yeah.
Absolutely, you could do it that way. Yeah. So I'm just doing it this way because this is sort of like the way that we used the most in the first way. But yes, you could set it up a different way. Absolutely. Okay. So we need to figure out some things. What's the equation here? What's the equation of the line? Well, first we need a formula just for the line.
It's under square root something.
Yeah. What shape? The graph is what shape? It's from a circle. What's the equation of a circle?
X squared plus y squared equals 1.
X squared plus y squared equals r squared. Exactly. Okay. Now, the way that we've set this up, as I already said, we're taking vertical slices. So we're going to be using dx. So if we set it up dx, that means x is our variable. So that means y is our function. So we're going to want to rewrite this so that y is a function of x. So y squared equals r squared minus x squared. Y equals the square root of r squared minus x squared. Now also note that by just writing square root, we're not taking the entire graph of a circle. We're only taking the positive part. But that's fine because that's the semicircle that's on the top, and that's actually what we want. So this actually just came out as the function of the exact part of the graph that we want. Okay. So now we've got the function for y. So now how do we use that to say what is the volume? How do you write down the formula for the volume? Yeah, it's going to be pi r squared. Okay, and what else do we need there? We're missing something very important here. Integral. Right. So the integral. And you're right, we also need the boundaries. So, first of all, are the boundaries going to be x values or y values? The boundaries are going to be x values because we set it up dx, so we're ranging over x values. X is our variable. Okay, so where is the first x value where this sphere starts? Yeah, the radius is r, so it goes from negative r to positive r. So let's fill that in on the picture. So negative r to positive r. So cool. So that's, we go from negative r to r. Okay. So notice that in this case, I'm using a typical convention of notation here, which is I'm using big R as a constant fixed radius, and I'm using little r as the radius function. Okay. So, integral from negative r to r of pi r squared. So we can do a couple things. First of all, the pi is a constant, and that can just come out in front to make it look nicer. And now what else do we need to do?
Simplify the r
Uh,
square root into r squared.
Yeah, well actually not just simplify, we need to say what r is. So what is the radius function? Yeah, because the radius is just the y value, and it is just the y value of the function. So you should be able to see that. There's too many lines here. Okay. So this is the radius. Radius as a function of x. Okay. So the radius is just y. So this is just going to be there's the radius, and you square it. Now this worked out very nicely because what do we get in there now?
R squared minus x.
Yeah. Those things just cancel. So you get r squared minus x squared dx. And now we're ready to do this integral, but this integral is the easiest integral in the world. So what do you get?
R to 3 over 3.
Check yourself. What's your variable?
X.
X. So what is the integral of r squared when x is your variable?
R squared x.
R squared times x. Because what is r, if x is your variable, what is r squared?
Constant.
R squared is a constant.
Do we always assume that everything other than our variable is a constant?
Yes, unless you're told otherwise. Exactly. And then what's this one going to be?
X cubed over 3.
Yes, now this is, x is the variable, so you get x cubed over 3. So we did the integral, and we're plugging in, x equals negative r up to x equals r. So you get r squared times r minus r cubed over 3. Hold on. Minus, now I got to plug in negative r. And then pi times the whole thing. So we work this out, and what do we get? R cubed minus r cubed over 3 minus, this is going to be negative r cubed plus r cubed over 3. And once again, always careful with the signs. Because you're subtracting, there's negatives in there, there's powers. Okay. So you simplify this, you get 1 minus a third plus 1 minus a third, and you get 4/3 pi r cubed. And that should look familiar as a formula that you memorize when you're doing geometry. And now we've proven it. Pretty neat, huh?